tanto qua. It's fine. Perfetto. Allora, vivi qui. Dov'è? Va bene così? Ok. Okay, I think it's okay. So through this example, even if we had an interruption, we understood a couple of important things. First, we need to, of course, define the problem we want to solve. Here, as a problem that we wanted to solve was we want to control the height of the water in the tank. Okay, for the same tank, we could have a different problem. We could be interested in controlling the output floor by if we had some actuation, etc. We looked for a simple mathematical model. In this mathematical model, for example, we had no friction of the fluid through tubes or things like this. And we didn't explicitly take into account other disturbances like the existence of evaporation or things like or leakages. Then we had to translate our real problem into, we want some quantity to be small. Here we said, okay, we want the error of the actual height of the level tank to be small with respect to the desired value. Then somehow we were able to design a controller. In this case, the controller was just a K. What is a K? Well, K is usually I represent a constant quantity or a gain. So this is like an amplifier. Okay. So you have the error getting into in the
con la tercera columna de la matriz deseada.
K, what comes out is K times a E of t. Just a multiplication by a constant quantity or a matrix constant quantity K.
Si lo corrige, pues es mejor porque...
Once you design a controller, you go back here and you simulate. You see what happens with your chosen controller without the model that you have been considering for designing the controller, but with a more precise model, a model which takes into account some other effects that you have been neglecting when you found your linear time invariant model. If everything still works fine, it will not work in general as well as what you thought it could work, because you are now applying a controller designed on a simplified model. You are applying this controller on a more complicated model. But we are going to see through linear approximations, etc., that some things will still be guaranteed. Okay. It's not just a question. I try and I see if it works. I need to be sure that under certain circumstances, my controller will still be valid. And then, as a last step, I'm going to implement this controller on the real system. Okay, so you see there are several steps between the design of a controller and the final project, physical project. So my plan was to start working also on the models. So we're going to spend just a few minutes to introduce a little bit more. And then I would like to spend the last part of the lecture introducing you with this MATLAB and Simulink, which we can already use to visualize things that we have just seen this morning, okay? So this is exactly what we saw previously, general mathematical model. We could represent this linear differential equation here, or set of linear differential equation like this. Let's interpret this. I have x dot, so I'm here. X dot is equal to the sum of two quantities, the sum of two quantities. The first one is a times x. So if I take x dot and I integrate x dot, I will have x. I take x, I multiply by a, this is a matrix multiplication. X is a vector, so this that we are showing as a simple line has multiple components in it. And so here I have ax. Similarly, if this is the input, I multiply the input or the inputs, if it's a multi-input system, and I have bu. Okay, so up to here, I have just rewritten x dot equal ax plus bu. Sorry, up to here. Also the integration. So you see part here and this corresponds to making the integral. And if you're making the integral, so you also know that you need to know the initial
Professor, oh shit.